Now, what else can X-rays be used for besides medical type imaging? Well, we can use this for diffraction of crystals in order to figure out what their crystal structure is. We talked about diffraction some a couple chapters ago, but this is another application. So for diffraction to occur, we must have very tiny spacing, and certainly in an atom we have very, very tiny spacing, so we need a very, very small wavelength wave in order to be able to tell the differences between those two different layers. So what does it look like? Here we have our X-ray tube, and we shine light through the crystal and it gets refracted, so we get points of light on this photographic film. And here is probably one of the most famous X-ray crystallography images. This is the diffraction pattern discovered by Rosalind Franklin. She was able to get this image, and it was later received a Nobel Prize. She didn't get it. Watson and Crick got it for figuring out that this meant that the DNA was actually helix shape. And how we knew this is a helix shape is basically we can think of these helices as being made of basically two planes at an angle, and where these cross gives us this characteristic kind of X pattern, and these angles then tell us how far apart each layer is as a function of the wavelength of light, as we think of each atom in this as basically creating a layer. So Bragg's law states that as the beam comes in and goes out, we'll have an incident beam and a reflected beam. The beam reflected from the lower surface travels a little bit farther distance than that of the upper surface. So this path difference is equal to some multiple of the wavelength of light, and so we can get m equals 1, 2, or 3. Typically we're going to use 1, and so if I know the wavelength and I know the angle, then I can figure out the distance traveled and figure out what the difference is between those two layers. So let's look at that DNA molecule and figure out if we can't figure out what the spacing is between those helix layers. So here we have a kernel of DNA. We know that alpha, the angle between the planes, is 40 degrees because we can see that on the X-ray crystallography. What is the lateral separation between the planes if this is observed using X-rays at 0.264 nanometers? So we use the Bragg's law equation and solve for d because we know the angle. We're just going to set m equals 1 and lambda. So we get d is equal to m lambda over 2 sine of theta is equal to 1 times r lambda, 0.264 nanometers. And I'm just going to leave it in nanometers. And we get 2 times the sine of 40 degrees will then give us 340 picometers. So that will be times 10 to the negative 12th. Next, we're going to look at this example. So here we have X-rays of wavelength. Again, we're given the wavelength are incident on a salt crystal. The first order maximum is observed at 8.15 degrees. Calculate the planar spacing based on that information. So I'm going to do basically the same thing. D is equal to m lambda over 2 times the sine of 8.15, and I'm going to get 0.55 nanometers.